Okay, so we've got the matrix 3, 1, 1, 1, 3, 1, 1, 1, 3. And what we want to do with that matrix is find its eigenvectors and eigenvalues. So we first of all have to form the characteristic equation. And if you remember, the characteristic equation was of the form the determinant for m minus lambda I equals 0. Now, I would point out, I do expect you to understand all the reasoning that went through, to, which was quite a lot of reasoning, that went through to finding that this was the characteristic equation that would find you invariant lines and the scale factors. Having said that, I think you just have to also learn that that is the characteristic equation. Because it's too much work to do every time to derive it from first principles. So you just learn that's the characteristic equation. And in this case, it would be the determinant of 3 minus lambda 1, 1, 1, 3 minus lambda 1, 1, 1, 3 minus lambda. And the determinant of that equals 0. Okay. Now, I will show you after this, one of the reasons we did factorising determinants was to find quicker ways sometimes of expanding the determinants that we get. But I'm not convinced, like a lot of you, I'm not convinced that it's worth the bother. So we are going to find the determinant of this equation just by expanding it without doing any factorising. And then I'll show you an alternative approach involving factorising the determinants at the end. Okay. So let's pick on someone, see if someone can write down the next slide. So Andy, can you tell me what the determinant of that matrix is?
So it would just be 3 minus lambda times 3 minus lambda squared minus 1.
Very good.
And minus 1 times 3 minus lambda minus 1.
Good, fantastic.
And plus 1 times 1 minus 3 plus lambda.
1 minus 3, 1 minus 3 minus lambda, 1 minus 3 plus lambda, yeah. Okay, and that's got to equal 0. So I think you can see there is plenty of opportunity for going badly wrong with the signs and the brackets there. So it definitely has to be done carefully. I think it's probably the easiest place to go wrong in this is in this step. Once you've done that, unless you've found any factors, which we haven't, you've got no choice really but to expand it out. So you can all do that at the same time as I'm doing it. You should be able to get it right. More likely to get it right, I would say, than I am. If you get to that step, you might be tempted to expand this cubic and collect like terms. But can anyone see, if you're still watching, you might not be, but if you're still watching, can you see something we ought to do first rather than multiply out to get a cubic? I'll tell you. I'm going to factor.
You get a factor of x minus 2.
Yeah, absolutely, yeah. So we factorise this, and we will be able to. I hope, by the way, if I've made a mistake, it's your job to spot the mistake. I know what the answers are supposed to be. I don't know if I'm getting those answers yet. So lambda minus 4, b minus lambda plus 2 is 0. 3 lambda plus 7 lambda minus 12 minus 10 minus lambda minus 2 That's right. Okay, so that's the answer I've got. I've got repeated root of 2 and is 5, and it is just algebra. It's just dealing with the cubic, but as you can see, it can potentially get quite difficult. You could potentially be talking about factorising a cubic. I will show you, I will put it in the content library later. I will just show you, just so you can see the basic idea. You might like to try a quicker method, but I will show you how you could have used factorising the determinant ideas. To give you the sort of idea, the sort of thing we can do, I've started off. I've started off with the same characteristic equation, but I've decided I'm going to aim to triangularise the matrix. Oh, actually, you can't see the board, can you? Can you see it?
I can see it. I can't see it.
Because you can't see that on content library. Okay, well, I'll put it into the content library later, but I'll point it out. You can listen along. What I've done is I've subtracted I'm trying to triangularise the matrix, and I just spotted a possible factor of lambda minus 2. So what I did was I subtracted the third column from the first. Something I'm not quite understanding about this new board, I have to say. I've subtracted the third column from the first, and that gave me a 0. And then I added the first row to the third. That gave me another 0. I then multiplied the middle row by 2 and the bottom row by 3 minus lambda, so I could then subtract the second row from the third, and that gave me an upper triangular matrix, which gave me almost straight away the answer. I am not, first of all, I'm not convinced that I've done it the best way by a long shot, but I've shown you the sort of idea. And secondly, even if I had done it the best way, I'm not at all convinced it's any easier than the first method. But it does depend on what the matrix is. Sometimes there's an obvious factorising determinant simplification that happens. So this is where something a bit fiddly happens. So this is why I need everyone here. I can just leave you to read this. Now we find the eigenvectors for each eigenvalue. We're going to start with lambda equals 5, because that's the easy one. We start with lambda equals 5. If you remember, what we're now trying to do is solve the equation m minus lambda I times u equals 0. Yes?
Sorry, when you're calculating the determinant, the first line, I don't quite get why it's a minus sign for like the middle bit.
Okay, so do you remember? So this is, you're going to need lots of practice. Yeah. Listen, guys, if you're sort of missing out a bit of steps and finding determinant to inverse, as I go through it, don't worry. Just make sure you've got your notes to hand when you're calculating the inverse. I think calculating the inverse is a routine that takes a bit of getting used to. But yeah, that answers the question. Yeah. So we're trying to solve that equation. With lambda being 5, that's going to give us minus 2. I can't remember it now. 1, 1, yeah. 1 minus 2, 1, 1, 1, minus 2, x, y, z equals 0. Okay, which gives me three equations, minus 2x plus y plus z equals 0. X minus 2y plus z equals 0. And x plus y minus 2z equals 0. Okay, there are three equations. If anyone thinks I've got one of them wrong, do tell me. I'm prone to making mistakes. And it might look like you've got three different equations. You do have three different equations, but they're not linearly independent. You can get one of those equations by combining two of the others. So what we've got to do is we've got to use these to find x in terms of y in terms of z. So it's just simple simultaneous equations. I think I'm going to start off by doing 1 take away 2. So I think, you know, more or less anything will do. If I do equation 1 take away equation 2, I get minus 3x plus 3y equals 0, which tells me x equals y. And then I can substitute that into any of the equations. I'll sub it into 3, but I could sub it into any of them because actually we don't need to use equation 3. We only need to use 2 of these equations. It's the way the eigenvectors come out. You will find that because 2 of them can be added or multiples of them can be added to find the third, you don't actually need to use the third. But because I feel more comfortable using all 3, I will. So if I substitute x equals y into 3, I get 2x minus 2z equals 0. So I get x equals z. Am I doing this in the right one? Am I doing this in the content library? Yes, I am.
Yes, you are.
Yeah, okay, good. Okay, fine. So, Michael then, so tell me what the, if the first eigenvalue is 5, what's the first eigenvector? We have actually found the eigenvector. Can you tell me what it is?
So we have it's k times 1 and what did we get for z?
X equals z. We got x.
K 1 1 1.
Exactly right. Good. So that means the line through the origin with direction vector 1. Yeah, sorry. That means that I'll try screen sharing next time. That means the direction vector that goes through the origin that's invariant is 1 1 1, and the scale factor of any point on that line would be multiplied by a scale factor of 5. Okay, a chance to ask questions. I know, okay, I think probably next time we'll talk about it another time, but maybe I should go into screen sharing because it doesn't seem to be working so well this time around for some reason. I'm not sure. Any questions on what we've done so far? No? No hands up, no questions. Okay. Right, I'd like you to try the second one for yourself, but I do expect you to have some problems. Okay, so when you come to those problems, let me know.
Sir,
Yeah.
is it just anything in that plane, basically?
Well done. Who's that?
Okay.
Kate. Yes. So we'll look at it, but that's right. What you find is you get an invariant plane, don't you?
Yeah.
So there's a number of different. So if you've come up with a plane as your answer, that's fine. If we've got to express this as a vector, you might find it challenging to work out how to express a plane as a vector. But you're exactly right. You have an invariant plane, and that's always going to be the case if you have repeated eigenvalues. That's what that means. Well, okay, I think that's what that means, that you're always going to get an invariant plane.
I don't quite get that.
Okay, so Ethan, what have you done so far then? You've got, oops,
Well, I've got the matrix here of all ones.
so 1, 1, 1, 1, 1, 1, 1, 1, 1, x, y, z equals.
X plus y plus z.
So you get one equation, don't you? Whereas before we were getting 3 equations. In fact, it was only 2 independent equations. So we could write x in terms, we couldn't solve. No, just normally if you have 3 equations, you would be able to solve and find x and y and z. I say normally, but you might be able to solve to find 3 equations here, to find unique solutions. Here we couldn't. We could find x in terms of y in terms of z, but we couldn't actually work out what x, y and z were. Here it's even worse. We can't even find x in terms of y in terms of z. So the point is, Ethan, x plus y plus z equals 0. That is a plane, isn't it? Remember all that work that we did?
Yes.
Yeah. So that is an invariant plane. Okay. In terms of a vector, well, has anyone got an idea of how to express it as a vector?
Could you do the direction vector of a line perpendicular to the line?
Okay, I mean, yeah, but if we put, well, I want to know the eigenvector, so you're right that you can define a plane by a vector perpendicular to it. But if I put that vector there, then it's not an eigenvector, is it? It can be used to describe the plane. I want to put something in there that's a vector, this is invariant. Any ideas? Put your little yellow hands up if you have any ideas. Otherwise, I'll start you off. Okay, I'll start you off. I'm going to put P as the x component of my eigenvector. Anyone like to suggest?
Just 3 P's.
I can't put 3 P's, can I? Because it's got to be x plus y plus z equals 0. Okay, well, I'll put Q for the y component. Now, you should all be able to tell me what I've got to put for the z component. Please don't say R. Don't say R. What?
Minus p minus q.
1 minus p minus q, yeah. So I think the bit that Kate got right at the start is that you've got an invariant plane. That's crucial to understand. It's a little more unfamiliar about how we can write a vector that lies in a plane as a single vector. So this is any vector this form.
So,
yeah.
why is it minus p minus q? Because wouldn't that give you 1 as the...
Sorry, I have absolutely no idea why I put that. Thank you. And it's not even, Ethan said minus p minus q, and I decided he must have put a 1 there. This form is x plus y. So I think to the extent that there's any difficulty here, if you've understood the concepts, you've obviously got to be really careful with the algebra when finding the eigenvalues. And I think this is the trickiest thing when finding the eigenvectors, what to do when you have repeated roots. So you might want to make a sort of note. I would regard this as the toughest bit. Okay. So I haven't shown you everything yet that you need for the next exercise, but I've certainly shown you